Okay, the binomial model. We're going to do some of the some simple ideas behind derivatives, simple derivatives valuation. And the easiest way to explain some of these ideas is to use a thing called the binomial model. Now, the binomial model is really no use for anything other than teaching purposes. Some people say things like it allows even MBA students to understand derivatives. That's the kind of catchphrase. But the point is, as a model, it's a bit messy to generalize. It's not totally realistic. As a numerical method, as a way of finding the number, the answer, the option value is 10.45, something like that. It's slow. It's not that slow. There are slower methods out there. We'll teach you some of them, and there are faster methods. What the binomial model is, it's a version of something called the finite difference method. The finite difference method can be very powerful. The binomial model can't. So be wary of that. If people boast about how they've implemented the binomial model for an American option, say, well, that's kind of, that's a piece of cake. We'll be doing that in seconds here. We're not going to do anything on laptops. We have done laptop work with the binomial model in the past, but it's a bit clunky. Instead, what we're doing is we're experimenting with just playing a recording of someone implementing the binomial model in a spreadsheet. The reason we do it in a spreadsheet is because it's nice and pictorial and you can see what's going on. You wouldn't, if you really had to implement the binomial model for some reason, then you wouldn't do it in a spreadsheet. But it's kind of, even though it looks pretty, you can understand it at the end, it's still a bit clunky to do. Hence, we're going to just play the recording and I'll commentate the recording. All right, so the binomial model. It starts with a very simple model for an asset price random walk. Now, yeah, it starts with a simple. It introduces you to the idea of delta hedging. Now, we're going to do delta hedging. Don't worry about the power thing. They're not going to be copying anything, so they don't need the laptops. It introduces you to the idea of delta hedging. Now, delta hedging is the real reason that Scholes and Merton got a Nobel Prize. That's the clever bit, delta hedging. You'll see how we use the idea of no arbitrage, and you'll see how all of this leads to a valuation model for options. Along the way, you'll see risk neutrality. Who's heard of risk neutrality before? Okay, a few of you, any distance people? Risk neutrality. Risk neutrality is, our pure mathematician friend's not here. It's one of those things that it's a concept, I suspect it's been invented by pure mathematicians to confuse people. It's a very confusing concept. You don't need to know anything about risk neutrality to do anything with derivatives. In fact, it would almost be better if you didn't know anything about risk neutrality. However, there are so many people out there who worship the concept of risk neutrality. If you say you don't know about risk neutrality, you won't be taken seriously. And it's quite a tricky concept. Anyway, I shall go through it, and you won't understand it. You won't understand it, by module 3. Maybe by module 4 you'll understand it. If you understand it by module 4, then you probably don't understand it. It's when you think you understand something that you don't really understand it. It's when you don't understand it, it's when you think you understand it and realize that you don't understand it, and then after that you learn to understand it. That's when you do understand it, if you see what I mean. So don't expect to understand it. Right, by the end of this lecture, you'll understand how hedging is used to eliminate risk. Hedging, as I say, this is the idea that won Scholes and Merton a Nobel Prize. It works beautifully in theory. It works beautifully in the binomial model, which is a very popular model. It works perfectly in the Black-Scholes model, which is obviously a very popular model. It doesn't work so well in the real world. Okay, it's one of those funny things that the two most popular models that people use are the ones that say it's okay, we can hedge perfectly, there's nothing to worry about. Once you move to more interesting models and once you move towards the real world, then you realize it doesn't quite work. So it's funny that there's a lot of that in finance, people doing things which make you think, oh, it's fine, CDOs, you know, we can hedge those, and things are not usually that fine. But I will explain that along the way. So you'll understand the binomial model, and you'll understand, well, you won't, the concept of risk neutrality. Okay. The framework. We're going to have a very simple framework. We're going to have just a stock that can go up or go down. And we're going to have a call option on that stock that expires tomorrow. This stock can either rise or fall by a known amount, a fixed amount. And just to keep things simple, we're going to have 0 interest rates to start with. We'll change this a bit later on. So this is the sort of picture we've got. We've got a stock. Let's say it starts off at 100 today, and it can go up to either 101 or fall to 99. So this is the essential part of this model that there's some randomness in here. And that happens over a period of 1 day. We're going to start doing this with numbers, then we'll introduce symbols and play around with what comes out of it. I'm going to say that there's a probability of 60% of the stock rising, and therefore a 40% chance of the stock falling. So 60% of the time the stock will be 101 tomorrow, 40% of the time it will be 99 tomorrow. And we have a call option on this stock. Call option with a strike of 100, and this expires tomorrow here. So if the stock rises to 101, what is the call option payoff? 1, very easy. 1. If the stock falls to 99, what's the payoff? 0. Very good. Which then, let's follow the obvious question. What's the value of the option? Any thoughts on the value of the option? 60p. We got 60p. You can play this at home. Any other thoughts about the value of this option? 0.6. Who says 0.6? What do you think?
Smaller than 0.6.
You think it'd be smaller than 0.6? Give me a number. 0.5999. Oh, okay, interesting. No, that's good. I like that because it's a possibility of discussion there. Any other thoughts?
If we're assuming no interest rate, then this 0.6 should be the risk neutral price.
If the gentleman on the front row is saying if there's 0 interest rates, then it should. The risk, you said risk neutral. Ooh.
Risk neutral.
Ooh. Do you think you understand risk neutrality?
Probably not.
very, very honest answer, and I can confirm that. No, the answer is not 0.6. It's not. Okay. Oops. The answer is 0.5. Okay. Now, it was a trick question. It's tempting, isn't it? It's very tempting to say, well, 60% of the time I'm going to get 1, 40% of the time I'm going to get 0, so 0.6 times 1 plus 0.4 times 0, what do I get? 0.6. And then you might, if you're sophisticated, you might say something like, well, I'll discount that to 1 day, but that doesn't matter because it's 0 interest rates. The problem with that, taking expectations, which is what you're doing there with that calculation, is that expectations is generally not the way to value things. This may be where your 0.59 comes in. But generally speaking, if you're going to invest in something that is risky, this is risky, right? This option could be 1, or you could lose everything. If it's risky, you want to be compensated for taking risk, right? There's a thing called modern portfolio theory that's a part of the CQF. So generally speaking, you'd say, well, I would pay, if I'm buying the thing, I'd pay less than 0.6. And maybe, is that where your 0.5999 came from? Or not? It's not. Where did your 0.5999?
Some discounting factor.
Oh, no, because interest rates are 0. Okay. So we scrub that one. All right. No, normally you'd say something like, well, I'm going to pay less than that. Because if I'm going to play this game, if I'm going to gamble on this option, I want a positive expectation. Okay. That's a general rule in finance. Is if you invest in something, you want a positive expectation at the outset. There are times when you don't. You know, people are not rational, or maybe you take part in a lottery. You know, if you need some operation and you're in America and you haven't got any money, then the only way to get some healthcare might be to buy a lottery ticket. Okay, so even though you expect to lose money, that might be your only chance of getting this life-saving operation. So that would be logical. But most of the time, one thinks you'd need a positive expectation. But usually, it's a kind of a risk aversion thing, or it's a personal preference. How much you need in compensation or positive return is a personal choice. But here, I'm saying it's not a personal choice. I'm saying the answer is 0.5. There might be some crazy, reckless gambler among you who'd say, oh, yeah, 0.599, I'll pay for this. There might be someone really conservative who says, oh, I don't like the look of this, I'm going to pay 0.2 for it. That would be a personal preference. I'm saying personal preferences actually don't matter. And that's very unusual in finance, that personal preferences don't matter. And again, that's part of the whole Nobel Prize winning thing. So let me show you where this comes from. It goes like this. We're going to, there's a trick, it's called delta hedging. We're going to construct a portfolio. And this portfolio is going to consist of the option. We're going to hold the option, and we're going to sell short a position in the underlying. We're actually going to sell half a stock. All right? So we had, one of the assumptions within all of this is you can sell fractions of things. So we're going to buy one option and sell half of the stock. Now watch what happens. The stock bit can go up to 101 or go down to 99. At the same time, the option bit of the portfolio goes up to 1 or down to 0. So let's look at what happens. If the stock goes up, then this portfolio, long the options, short half of the stock, becomes worth 1. 1 from the option, and the stock position is worth minus a half times 101. So what's that? That's 2 minus 101 over 2. That's equal to minus 99 over 2. So if the stock goes up, the value of our portfolio is minus 99 over 2. If the stock goes down, we have 0 from the option, and we have minus 99 over 2, because we've got half a stock position. We're short, so minus a half, and the stock is worth 99, so minus 99 over 2. Now, what do you notice there? Well, the thing that you notice is that whether the stock goes up or goes down, the portfolio is worth exactly the same. That's hedging. In other words, we could have just bought the stock. That's risky. You make $1 or you lose $1. Or you could buy the stock. Sorry, buy the option. You make some or you could lose some. Here, we've got a portfolio that we don't care what happens. We've hedged. That means that the portfolio value today, which I've called here, I've got it down here as V, meaning the unknown option value, minus a half times the current stock price, that must be equal to the minus 99 over 2. There's no discounting. Interest rates are 0. We know that tomorrow this portfolio is going to be worth minus 99 over 2. So the portfolio today must also be worth minus 99 over 2. Okay, we're not talking about credit risk or anything like that. So that means that this V minus a half times 100 must be equal to minus 99 over 2. Just taking the minus 50 over to the other side, and you end up with the option value has to be a half, 0.5. All right? And the interesting thing about that calculation is if we look at the original model, which information on that page did we not use?
The probability.
Yeah, we didn't use the probabilities. So that's what we're starting to get into the world of risk neutrality. When we talk about risk neutrality, these probabilities don't matter. So when you did that calculation, and you called it, what did you call it? A risk neutral something? Yeah. It wasn't, because you were using these probabilities. You're going to see things like, this is called a real probability, which is sort of self-explanatory, what that means. Shortly we'll be seeing a thing called risk neutral probability. So what comes out of all this is the idea that we don't care whether the stock goes up or goes down because we're hedging. That's like saying that the growth rate is irrelevant. The very first lecture, when we did the spreadsheet stuff and we calculated from that S&P 500 index, we calculated a growth rate, a mu, and the volatility sigma. Turns out that we spent all that time trying to calculate mu. We don't need it. If we're valuing options, we don't care which direction the stock is going. I think that's on another page, but I'll mention it now so that distance people can hear that. Suppose you have two stocks. Two stocks, both are worth 100.
100.
Both have the same volatility. Here it says volatility does matter. Okay, volatility. Both stocks have the same volatility. They have the same value. They both have options, call options on them that expire the same day. They have the same strike. The same currency, so they've got the same interest rate. Everything's the same. The only thing that's different between these two stocks is that one stock is doubling every year and the other is halving every year. Options on those are the same value. It's very counterintuitive, but options have exactly the same value.
So why it would be like that?
Say again?
Why it would be like that? Like
Well, because it's like that because the direction the stock is going has been hedged out. It might be that because you see one stock is rising and the other is falling, you might say, well, I'm going to buy the option on the one that's rising. Yeah, and you'd make lots of money if you turn out to be right. But the theoretical value is the same for both of them. We short half a stock to do exactly what I did there. Is your question, why do we short something, or is it why do we short a half? That's coming up very shortly. And yeah. You can't do 100 and 0.
Okay.
You can do anything. You can do 0.99999, 99.99999%. You can't hit there's a singular, because if it's 100% and you've got risk-free at 0 and you've got 1% in one day guaranteed, then you've got a kind of an obvious arbitrage. So forget, who cares about options when you've got that. So it's a sort of singular thing. Point that.
All of this is assuming no volatility skew. Is that right? Because if you have skew...
You're mentioning volatility skew now? Because it's a bit premature. Can we go on? What's your question?
Well, your price won't be the same for the top side and the low side if you...
No, the value depends. The value depends upon the strike. You can do a different calculation with different strikes and things. You get different numbers.
But if each strike is a different volatility.
That doesn't make any sense. That you're running before you can walk. Did you get the answer 0.5?
No.
In that case, shut up. Sorry, he's asking me about volatility skew, guys. Help me out here. No, we'll come on to that sort of thing. But you did use a word, an important word there, price. I'm talking here about theoretical value. Now, this is where I'll introduce it with you guys because you're clearly very bright. I think in terms of three things: value, price, and worth. Worth's a bit nebulous, but price is easy. Price is what you see on the screen. Price is what you can buy something for. In a shop, it's the price. You don't talk about the value of something in a shop, do you? I mean, yeah, you do. In American shops, they talk about, $99 worth of value for 10 cents or something like that. They talk about that sort of value. But value in this context means a sort of theoretical value, a number that you come up with according to some theory. Worth is sort of, well, how much is it worth to you? If you're the person buying the lottery ticket because you need the operation, then that lottery ticket is worth a lot. It's worth a lot to you. It has a price of, let's say, $1. It has a theoretical value of, say, 60 cents, because I don't know how much you lose typically buying a lottery ticket, but let's say it's 40%. But it has a worth. That's a life-saving operation. And so you would, even though you expect to lose money because the value is less than the price, it's your only chance. So that's what I mean by a bit nebulous. But it's important. I think it's important to distinguish between value and price. Here, for the moment, we're talking purely about theoretical value. Obviously, the real world is subtly different from that. But for the moment, just think in terms of maths and theoretical concepts. Once you move into the real world, you've got to start tweaking things a bit, or you should tweak things a bit. Anyway, volatility matters a lot. Why should the theoretical price be the market price? One question. That is what I mean by that is, okay, I've come up with a theoretical price of 0.5. How does the market, the value, how does it, does the market know to price it at? Well, the idea goes like this. If somebody is selling this for, suppose it's, somebody sells it, well, okay, I'm going to try, we all have the same information. 6% chance of rising, 40% chance of falling, 101, 99, you've got all the same information as me. I'm going to sell you an option. I'm going to try and sell you an option for 0.7. Is anyone going to buy it? Well, apart from the person who needs the extra 30% because of a life-saving operation, generally speaking, no one's going to buy that because you expect to lose money. Would anyone pay 0.6 for it? Again, why bother buying the option? It's a biased coin toss. There's no positive expectation. Would anyone buy it for 0.55? You might. If you like taking a bit of a gamble, you're probably going to make your payoff is probably still going to be 60. The expected payoff is still 60 pence or 60 cents. Okay, because that calculation you did, all of you who did the 0.6 calculation were right in the sense that's how much you expect to make. It's not the value of the option, but it's the expected payoff. So you might perfectly well say, well, I'm going to pay, if somebody's trying to say, Paul's trying to sell me this for 0.55, then I'll buy it because I expect to make 5 cents.
It's
Okay.
not true that over a long time, if I keep buying lots of them, I'll still expect to make 50 more.
Exactly. If you buy lots of them, this is not your one deal. You're going to be doing this every day. Central limit theorem, something will kick in. You're going to make lots of money. Now, I'm happy. If you want to pay 0.55, I'm very happy. I'm very happy because I am doing this delta hedging. I sell the option to you, and I will buy a half of the underlying stock. I've just changed signs there. Instead of buying the option, I'm now selling the option. To hedge it, I will buy 1/2 the underlying stock. That means I have no risk. It's exactly the same picture as before, but with the signs changed. So I have no risk at all. And that means, to me, the option has a value of 0.5. I've just sold you for 0.55. So I am guaranteed to make 5 cents. 0.55 minus 0.5. I'm guaranteed to make that. You expect to make 5 cents. Okay? Fine, we've got a nice little business going here. I'm making 5 cents every day. You're making, on average, you're making 5 cents every day. And then somebody else comes along, somebody who knows about risk neutrality. You contact him and you say, I'll let you have it for 52 cents. Okay? You start buying off him. Now you're making 8 cents. You're making more than with me. You were my loyal customer for all those years, and he comes along with his burgundy-colored jumper and sells it for 52 cents. You're making, but you know about hedging, so you are making 2 cents. I'm making nothing. So I come back with, all right, 51. That's my best offer, and then you come back to me, and you come at this point. You see, it sort of converges. It's weird. It's a weird business model. The value, sorry, the price converges to the value, at which point.
So basically, it's market forces. So
It's sort of a market forces thing, but it converges to the point where we say, forget it. We'll do something else. We'll make shoes or something. Like Daniel Day-Lewis will go and make shoes, and then you can't buy any options from anybody. It's a weird. That's a sort of weird economic thing, where everything moves to such efficiency that nobody bothers to do any trading. Yeah. You're looking ahead in the notes. I'm going to come on to that. Don't. I'll come on to that in a second. So that's why it converges. It's a sort of market forces argument, is why it should converge. How did I know to sell 1/2 of the underlying? Other than I've done this lecture far too many times. So the way we do it is like this. I'm going to introduce our first symbol. Here we go, delta. And it's called delta hedging. I'm going to set up a portfolio that's got the option with the value V, selling short delta of the underlying with a value of 100. Tomorrow the portfolio is worth either 1 minus delta times 101 if the stock goes up, or 0 minus delta times 99 if the stock goes down. All I have to do to make sure that I have make the same amount of money whether the stock goes up or goes down is just make those two things equal to each other. The payoff in the two situations.
why did you make it equal to each other?
Because why did I make it equal to? This is how much I make if the option goes up. Sorry, the stock goes up. This is how much I make if the stock goes down. Hedging is all about making those two things equal, so that regardless of what happens, I get to sleep at night. All right. I don't care whether the stock goes up or goes down. So I just make those two things equal to each other. If I do that, what comes out is delta is 0.5. Okay. Where that comes from is it's just the range of option values divided by the range of stock prices. So later on, when we go over to continuous stuff, rather than this discrete stuff, you'll start seeing things like dV by ds, which is just how much the option price changes divided by how much the stock changes. There, like that. So let's do another example. The stock is 100, it can rise to 103 or fall to 98. Still interest rates are 0. We go through the same sort of argument. This is the position, we don't know what delta is. If the stock rises, then we have 3 minus delta times 103. If the stock falls, we have 0 minus delta times 98, because it can rise to 103 or fall to 98. Equating those two gives us delta is 0.6. And then if the stock falls, or whichever way the stock goes, up or down, you're going to have your portfolio is worth that much. So you just set that equal to the value of the portfolio today, and that gives us V is 1.2. So you can do this depending, whatever the model is, you can get do the same sort of calculation. If interest rates are non-zero, it doesn't make that much difference. Let's have an interest rate of 10%. So we're going to have a discount factor. This is over 1 day, remember. A discount factor of your 0.9996. That means that if the stock, well, what we find happens is actually that doesn't change the delta at all. Delta is still 0.5. All we do now is take the payoff tomorrow, which is still going to be minus 99 over 2, but multiply it by the discount factor. And that gives us a slightly higher option price. Okay? So that was really easy, all trivial. Now we come to your question, which is, suppose the stock can rise to 101, probability 0.6, fall to 99, probability 0.4. What if we can forget everything I've been saying for the last half an hour? Suppose you didn't see this. You would say the stock price is, what would you say the stock price is? Doing your expectation, your incorrect option. So your incorrect expectation calculation. What's 0.6 times 101 plus 0.4 times 99? It's 100.2. The easy way to do that is to forget the hundreds. It's just 0.6 times 1 plus 0.4 times minus 1. And the answer is 100.2. Okay, so even there you can see that actually the stock is incorrectly priced. Well, it's not. The average stock price tomorrow is 100.2, but it's risky. So you should pay less, 100. That's what the market has somehow decided is the right value. Okay, the market has somehow decided the right value is 100. That you need a 0.2% compensation for taking the $2 of risk. So if the calculation is wrong for the stock, well, it's going to be just as wrong for the option.